In this video, we'll use the concept of Kb to calculate the pH of weak base solutions. But first, let's review the Bronstedlowry definition of a base. The Bronstedlowry definition of strongest base must be the OH ion. They're going to attract hydrogen ions strongly to produce water. Everything else is a weak base, and they do not attract protons or hydrogens as strongly as OH. Even amongst the weak bases, there are still some bases which are stronger than the others. In order to find which one are stronger weak bases, we can look again at our relative strength of acid and base table on page 8 and 9 of your data booklet. You'll notice that at the very top row, it says that conjugate bases are listed there as well. It is actually next to the right of the acid formula. Also note that the strongest weak base is at the very bottom of the table, so strongest weak base, and the weakest weak base is listed at the top of the table. At the very last column in your table, you'll notice that there's a Ka value. However, it does not show the Kb value. We can calculate the Kb value by rearranging our equation Kw equals Ka times Kb to solve for Kb now. So then Kb equals Kw divided by Ka. Let's look at an ice table for a strong base. So a strong base, such as a metallic hydroxide, such as NaOH, dissociates 100%. So if you have initial concentration of 0.10 mole per liter, at the end of the day you have 0 NaOH. It has all been dissociated into sodium ion and hydroxide ions. However, for a weak base, this dissociates or ionizes less than 100%. So for example of sodium acetate, this reaction only happens to 6.3 times 10 to the minus 3%. So if the initial concentration of acetate is 0.10, at the equilibrium you have a concentration of 0.1 minus 6.3 times 10 to the minus 7 moles per liter. If that much acetate has reacted, you also get the same amount of acetic acid and hydroxide. We will now officially introduce the equilibrium constant for the base reaction, also known as the Kb. This is a way to measure the strength of the weak base, and we're going to measure it by the amount of reaction with water in dilute aqueous solution. So this is called the base ionization constant. And the Kb is going to be set up the same as Kb, which is to say that the Kb is equal to the concentration of the conjugate acid and the concentration of the hydroxide multiplied together, divided by the concentration of the weak base. So let's look at a quick example. We have a solution of sodium citrate, and the reaction for aqueous sodium citrate is denoted as such. The equilibrium expression will be the concentration of the conjugate acid, denoted here, multiplied by the concentration of the hydroxide, divided by the concentration of our weak acid, our citrate. Let's now look at an example with numbers. It says a solution containing 5 grams per liter of aniline, and the formula is right here, was prepared, and the pH was found to be 8.68. Calculate the base ionization constant, the Kb, for aniline. And we're given the formula for aniline and the concentration in terms of grams per mole, and we're told the pH is 8.68. The very first step we need to do is to determine the concentration of the aniline. So we know that we have 5 grams, and we can calculate the molar mass of aniline to be 93.12. So if we divide 5 by 93.12, our units cancel, giving us moles per liter, the units for concentration. Our second step we need to do is determine the concentration of hydroxide. We're told the pH is 8.68, however, we can find the pOH by subtracting the pH from 14. In this case, it is 5.32. Now we raise 10 to the power of negative 5.3 through to find out the concentration of hydroxide is 4.8 times 10 to the minus 6. This is our equilibrium concentration of hydroxide, which we can put into our ice table later. But first we need to set up our ice table. Luckily for us, all of the coefficient here is 1, so we do not have to worry about any exponents in our equilibrium expression. Again, we do not include water because water is a pure liquid. We just calculated the initial concentration of aniline was 0.0537. Initially there was none of the conjugate acid and none of the hydroxide. We know that at the end of the day we have a concentration of 4.79 times 10 to the minus 6 moles per liter of hydroxide. Well, how did it get there? Oh, it must have reacted, or it must have changed through a concentration change of positive 4.79 times 10 to the minus 6 moles per liter. If that much hydroxide was produced, then the equivalent amount of conjugate acid was also produced. And if that much hydroxide was produced, we use the same amount of the weak base. So then at the equilibrium concentration of the weak base, we can calculate to be 0.0537 minus 4.79 times 10 to the minus 6. And the concentration of the conjugate acid is still 4.79 times 10 to the minus 6, and same for our hydroxide. We can now substitute in our value into our equilibrium expression using the values that we just determined in the ice table. We do our math and we find that the Kb is 4.3 times 10 to the minus 10. It is reasonable for a weak acid because it's relatively small, and our final answer should have 2 significant digits, which it has. Another type of example that deals with the Kb is that we can be given the Kb and then we can calculate the concentration of hydroxide, or to take it further, to calculate the pOH of a solution. Now remember, Kw equals Ka times Kb. This is useful because in our table of acids and bases, we're only given the value for Ka, but we do not know the value for Kb. And remember, the value for Kw is 1 times 10 to the minus 14. Let's look at a specific example. Here we have quinine, a white crystalline compound. The base ionization constant, so Kb, is 3.3 times 10 to the minus 6. What is the hydroxide concentration and the pH of a 3.6 times 10 to the minus 3 mole per liter solution? Here in this case we are given the Kb, so therefore we do not need to use the formula Kw equals Ka times Kb to determine the Kb. And now we're asked to find out hydroxide concentration and the pH. As usual, the very first step you need to do is to determine the balance equation. Again, luckily for us, all the coefficients in this balanced chemical reaction are 1. And once again, we do not worry ourselves with water because water is a pure liquid and it's not included in our equilibrium expression. We are told that initially we have a concentration of 3.6 times 10 to the minus 3 moles per liter of the quinine. And initially we have none of the conjugate acid and none of the hydroxide. For the change row, we know that a certain amount of quinine will be reacted. Therefore, the same molar or same concentration of the conjugate acid will be formed and the same concentration of the hydroxide will be formed. Therefore, for our equilibrium, we know that we have 3.6 times 10 to the minus 3 moles per liter minus X of the quinine and X moles per liter of the conjugate acid and the hydroxide. If we were to set up our equilibrium expression right now, we will realize that we have a quadratic equation. So we can now apply our simplification rule to determine, can we determine this is to be a negligible amount and make this into a 0? And we'll do that next. So similar to weak acid equilibrium questions, the criteria that we can use to determine if the X is negligible is to determine if the concentration or the ratio we get when we divide the concentration of the weak base divided by Kb is greater than 1,000. In this case, we find that it is greater than 1,000 indeed, so therefore we can say that X is a negligible amount and not worry about the subtraction in the denominator. So instead of writing 3.6 times 10 to the minus 3 minus x in our denominator, we can just write 3.6 times 10 to the minus 3. So here is our simplified equilibrium expression, and now we can go on and solve for x. The first thing we need to do to solve for x is to multiply both sides by 3.6 times 10 to the minus 3. So now x squared equals 1.188 times 10 to the minus 8. Square root both sides, so x is 1.09 times 10 to the minus 4. This is equivalent to our concentration of hydroxide. Therefore, from that value, we can determine the pOH by taking a negative log of 1.1 times 10 to the minus 4, and we find that our pOH is 3.96. And the last step is to find the pH, and we can do that by 14 minus the pOH, and we find that the pH of our quinine solution is 10.04. Notice that pH is above 7, which means it's a basic solution, which is good because we know quinine to be a weak base.